Isn't that recording? Oh, it is recording. Okay, here we go. We are finishing 4.6 today. Just two more examples. I'm going to name them example 4 and 5 because that's what they're named in the text. So I'm pulling these straight from the textbook. If you'd like to go, remember that you have the ebook, right? So you can go and look at these examples later if you don't want to write everything down. Or you could pull the ebook up while we work them. Really, that would be the most ideal thing. So what this is the plan. We're going to do this example. We're going to do example 5, which are both going to be population model problems, both relying on either the exponential growth rate, the relative growth rate exponential function, which is the one that has a base of e, or the model for a population that is doubling that has a base of 2. So remember that those two formulas are going to be in your formula sheet, and the problem from this section 4.6 is going to be one of those, right? So we're going to talk in particular in these two examples about how do you know which one to use, right? And there's going to be some really obvious like keywords, like for instance in this one it says relative rate of growth. So anytime you're dealing with a population growth that has a rate of growth that's relative to the population size itself, you're going to use that relative growth rate formula. And the other one, if it says anything about like example 5, it says something about the number of bacteria doubling every 40 minutes, then clearly, you know, you're going to use the formula or the function model that has that deals with doubling, right? A doubling growth rate. Doubling time is what the text calls it. And then Friday was, yeah, Friday, we're going to review, because there are two things in addition to all of chapter 4, which we've spent the past month or however long covering. In addition to that, you also need to know 2 particular topics for the final exam. One of them is solving quadratic equations, so we'll review that on Friday, and also knowing transformations of graphs of functions. So like what it does when you add, subtract, multiply, divide, inside and outside of a function, what negatives do to the picture, that kind of stuff. So we'll review that on Friday as well. But today, let's start with example 4 from 4.6. So this is still 4.6. Example 4 says in 2000, so that's the year 2000, the population of the world was 6.1 billion and the relative rate of growth was 1.4% per year. So when I see relative rate of growth, I'm immediately thinking, okay, I need to be using the model for population at some time that looks like this, as opposed to the one that has a base of 2, right? So just to remind you that that one that has a base of 2, well, I don't really want to write it here because we're not going to use it. I'll write it up here, just so you recall what it is. They both start off looking the same, little n sub 0 to represent the initial amount, and then 2 raised to the t over a, where a is that doubling time. But that's not what's happening here. That's why I stuffed it up in the corner. We're not using that one. We're going to use this one, where r is going to be our percentage that was given that we'll have to turn into a decimal, and n sub 0 or n naught is going to be the initial population, which in this case is 6.1 billion. But let's keep reading the problem. It is claimed that a rate of 1%, so we have 2 rates here, so we're going to have to figure out what's going on there. 1% per year would make a significant difference in the total population in just a few decades. Test this claim by estimating the population of the world in 2050 using a relative rate of growth of, so we're given 2 different rates And what we're supposed to do is use the different rates for two different calculations here. So I'll call this part A then. Both of them are going to use the same model though, just with the same base model, right? With the base of E. So first, for part A, I need to note that R is going to be 1.4%, but of course, writing that as a decimal to be able to plug it into my model, always have to write these percents as decimals. And naught is going to be 6.1 billion, which so at this point I have to decide how I'm going to deal with that billion. I can write it all out. You know, I could say like 6,100,000, you know, write it all out. But I think I'll just write it like this. And then in the end, when I get my final answer, my output at time t, which we need to talk about what we're going to plug in for t as well. I need to remember that at the end, I just need to tack on billion, right? I need to remember to do that at the end instead of dealing with all the extra zeros and stuff like that. So by the way, what will t be? Well, they gave us the initial population at the year 2000, and they want us to measure it 2050, so that's 50 years. 50 years, right? That's the time difference that we're talking about here. So this is what's going to get plugged into the model, but first I need to build the model by plugging in that R in that N naught value. So I'm going to say N of t is equal to 6.1 times E raised to the 0.014 times t. So that's 0.014 times t. That's my model or function or formula for part A here. Now I'm going to actually calculate what they wanted. So plugging in 50, 0.014 times 50. And that's when I go over to the calculator to get a approximate answer, because this would be the exact answer, but that's, again, kind of meaningless when we want to talk about populations, right? So I'm going to say 6.1 times E raised to the 0.014 times 50, close that, and I'm getting 12.2. I'll say 12.3. And I need to remember to write billion at the back here, because this is a population of the whole Earth, and so that's I'm recalling that all of this is being scaled up to billion. All right, so now I basically do all that again except for part B, so with a different rate. So my function model then would be N of t is equal to 6.1, same initial population, E raised to the 0.01 times t, right? You see why that is? Because, so let me say this is R1, yeah. R2 is 1.0%, which is the same as 0.01. That's it, right? I could put another 0 at the back, but it's not necessary, right? So that's my R there. And oops. And the time span is the same, right? Because I'm trying to compare them directly. So I don't want to change the time span. It's still 50. So I'll say E raised to the 0.01 times 50. Just plugging in 50 into the function. That's literally it. And then, in fact, well, never mind. I thought I was going to be able to do this calculation easily in the calculator, like just replacing the rate. But I'll just retype it. 6.1 times E raised to the 0.01 times 50. Close that parentheses, and I'm getting. I'll write it right here. 10.1 billion. So this is all we were asked to do, just to calculate each each population based off of the two different rates, the two different relative rates of growth per year. The claim was, scroll down. It is claimed that a rate of 1% would make a significant difference in the total population in just a few decades. So is that a significant difference? Yeah, that's like 2 billion people, right? So just that little bit of a change in the percent, just 0.4% difference, gave us 2 billion more people. But, you know, really what we were asked in this problem is to do the math, and that's what we did. So just to recap the bigger points here, you got to know which model you're supposed to use. Out of the two population models that we're looking at, the relative rate of growth model and the doubling time model, we have to look for keywords like relative rate of growth and looking for percentages to know that we should be using this model. Then it's basically just plugging stuff in, right? You got to plug in the rate, so just make sure that you are converting that to a decimal appropriately. Remember, just divide it by 100. That's how you get it as a decimal. Make sure you're plugging in the appropriate initial population. And also make sure that you might have to do a little bit of thinking to think about what the time should be. But that was fairly straightforward here, just looking at the 2 years that they gave us, 2050 and the year 2000, and just subtracting to get that time span. Okay. Any questions about that one while I pull up the next example? Okay. So example 5. Says a culture starts with 10,000 bacteria and the number doubles every 40 minutes. Let me get rid of, I'm not doing part C. Part C is a graph question. I'm not doing that. I need to write part B real quick. So this is an interesting one because it's asking us to actually find two different models. So in the real world, when do you use one model versus the other? And that's going to come down to how basically like what kind of question you're asking and how the population is acting. So this one is kind of, you know, okay, if you're approaching this problem as a, you know, as a math student, you should use the doubling time formula because it's talking about a population that's doubling, right? So there's the key word there, doubling. So I would immediately lean towards this model here. And in fact, that's what part A asks us for. Now, part B is asking us to force it into a relative rate of growth form. To do that, we're going to have to figure out what is the relative rate of growth, because we weren't given that. We were given doubling time, not how much it's growing relative to its original size. So that'll be an interesting problem, but any sane person, I think, would just use the doubling time model, unless you were running a problem like this, doing a research project, and you needed it to be in terms of relative rate of growth for who knows what reasons, who knows what biologists get up to, right? So first, let's do the more natural thing and build it in this form. So I'm just going to write that down first. Okay, so I'm going to say n of t is going to be equal to initial population first, so that's 10,000, times, so that's times, that's not a decimal point, that's a multiplication operation there, 2 raised to the t, so nothing's getting plugged in for t unless they tell me to plug something in for t, right? They're not asking that here. Over, now, I need to decide what units, so, oh, I see, okay, never mind, sorry. Okay, this is measured in minutes, right? So I might naively just say, I might just say is A equal to 40 minutes, because A is supposed to be doubling time, right? A is doubling time. So yes, A could be 40 minutes, but the answer in this case is actually no, but only because why is that? It's a subtle thing, but only because the question asked for the model to be measured not in minutes, to be measured in hours. Okay. See that? T hours. So instead of just popping in 40 right there, which we could do if we were building this model without like the restrictions of a, you know, a math class example, we could put 40 there and just say that our model is measured in minutes. And if anyone has a problem with that, we could they can convert it to hours if they want to, right? But since we are required by this problem to write it in hours, let's do that. Plus, it's good practice to see how to do it. So how do I write 40 minutes in hours? Well, I can use a little bit of dimensional analysis, which you'll find to be one of the most useful things that math can do for you in your science classes. Changing units. So I want to get it measured in hours, so I put the unit of hours up top, and I want to get rid of minutes, so I put those in the bottom. Then I have to think about when are these two units equal to each other? Well, it's at 1 hour equal to 60 minutes, right? So that's the that would be the conversion rate right there. So then minutes, the unit literally cancels like a number, and I'm just left with 40 over 60 hours. But that reduces very nicely to 2/3. You know, cancel a factor of 10 and I end up with 4 over 6, and then 4 over 6 reduces to 2 over 3. So that is what gets plugged in for A, 2/3, which looks a bit messy. So we'll probably clean that up because that doesn't, you know, fraction over fraction in there. We don't like that. So let's clean this model up a bit by saying T over 2 over 3. So I'm just isolating the exponent up here because I'm going to clean it up, is equal to T times 3/2. Just recalling that rule, when you divide by fractions, you flip the fraction and flip the operation to multiplication. So that's the same as 3t over 2, just by multiplying the t up by the 3. And if you like, we can say 1.5t, if you like that better in decimal, because that's what 3/2 is, it's 1.5. So if you like it better in decimal form, we can do it that way. I would only write it in decimal form if it's a nice, clean, terminating decimal. Like I wouldn't do this for like 1/3, because 1/3 is a bunch of 3's repeating. You know, this is only appropriate if the decimal is nice and clean and terminates. I'd say more often it's safer to leave it in its exact fractional form. Okay, so finally for part A, after figuring out that thing about the doubling time being needed to be measured in hours, and then messing with the fraction, you know, arithmetic up here in the exponent position, getting 10,000 times 2 raised to the 1.5t, 1.5 times t. There it is. That was what this part A was asking for, was this this model. And this would be the natural model, I think, because the question was posed with a doubling time. Okay, but part B asked us to find a function, now force it into this relative rate of growth form. So let me give you a second to get caught up on any of this if you need to before I start part B. All right, so part B is going to be a little bit more tricky. Oh, I need the, hang on 1 second. So what are we doing? We need to force the model into a relative rate of growth form, which, by the way, that is the n of t equals n naught e to the rt. So what are we missing? Like, e is just a number, n naught we have is 10,000, t is some input, so it's the r. We need r. We need that relative rate of growth. We need r. Okay. So how do we find r here? Okay. What we can do is we're going to find, based off of the other model, based off of the model we just built, which where is it? Here it is. Based off of this model, we're going to find the population at some time other than 10,000, right? Because we already know at time 0 it's 10,000. We're going to find the population at some other time, and we're going to, so then we'll have two populations, and then we'll compare them to be able to get the relative rate of growth. So that'll be the plan. That will be the plan. So we need the population at some time other than time 0, because we already have the time 0. That's initial population, other than t equals 0. So what's the next, like, easiest choice? Just let t be 1. Let's measure the population after 1 hour. Let's pick time to be 1 hour. In other words, t is equal to 1. So use the model that we just built to find this population after 1 hour. So we'll say n of 1 is equal to 10,000 times 2 raised to the 1.5 times 1, which of course will just be 1.5. And this is going to give us a new population. And then once we have this new population, we can compare it with the original population of 10,000 to get a relative rate of growth. So I'm going to have to say approximately here, 28,284. I'll just round there, right? Rounding to whole numbers when we're dealing with populations. Okay. So now we have two population sizes, and we need the relative rate of growth between them. So how do we find that? How do we find the relative rate of growth? Well, now we go back to this formula. And we know what the population, according to our first model that measures the population for any time we pick it, we choose, we know that after 1 hour, it outputs this much. So I'm going to write this in blue now just to kind of keep it separate now. So we're going to the next model now. So I'm going back to n of t is equal to, I can go ahead and say 10,000 e to the rt. We're about to solve for r. That's what we're about to do. I know that at 1 hour, this should end up being 28,284. So I'm going to say 28,284 should be equal to, these models should tell us the same thing, right? R, and then at what time did this population happen? At 1 hour. So I say times 1. T is equal to 1. So I'm plugging in 1 into this formula and saying that this should be its output. Okay, and then I just solve for R. This is the hard part, really. Thinking of it like this, and you really have to know how functions work, thinking in terms of inputs and outputs and what should get plugged in where. But if you reach this point now, all you're going to do is solve for R, which will seem relatively easier, I think, because we've been doing it a whole lot. But I'll grant you that the hard part is getting up to this point to be able to solve, to build all of this up so that you can solve for R. So anyways, let's go ahead and solve for R. I'll divide both sides by 10,000. So I'll say 28,284 over 10,000 is equal to e to the R, because R times 1 is just R. And let's come over here, and I'm going to take a natural log on both sides to get, so remember, R is buried up in the exponent position. I want to get it out. So I take a log on both sides, and I want to cancel out the e, so I pick the log that has the same base, a base of e, that's the natural log. So I'm going to take natural log on both sides, which in here is going to give me some crazy number. And this will just be equal to R, right? Well, really, well, I'm kind of out of room here. What's happening in between here? Ln of e to the R just pops out R, right? So that's how R just came out here. I'm taking natural log on both sides, which of course the natural log and the base e cancel each other and just pop out that R. Let me flip this around and find my approximate answer. Ln of 28,284 divided by 10,000. I'm getting 1.0397. I'm going to keep a few digits of that, so I think that'll be enough. So finally, I'm ready to write the model that they want. They wanted this model to be forced into a relative rate of growth form, but I needed R to be able to do that. So now I'm ready to write the model. It should be N of t is equal to initial population times e raised to the R, which is that 1.0397 times t. Whoops, there we go. The point is, so what's the point here? These models tell us the same thing. So if we give them the same inputs, they'll output the same thing. And what two models am I talking about? The N of t is equal to 10,000 times 2 raised to the, oh crap, what was it? 1.5t. Oh man, I really messed that up. Hang on, let me write it a bit cleaner. N of t is equal to 10,000 times 2 raised to the 1.5t is the same as N of t equals 10,000 raised to the, times e raised to the 1.0397t, which is really interesting, but they're the same model. They're the same. Because the data that gave me my relative rate of growth here for this one came from the doubling time model. So both of these would be legitimate models for the original problem of modeling, where did it go? Modeling bacteria population that doubles every 40 minutes with an initial population of 10,000. So what's going on? Both of these are the same models, right? The much more natural one that just pretty much popped out at us was the doubling time model, because that's how the data was given to us. It was given to us as a doubling time, right? So this one very naturally just kind of popped out, just plug stuff into the formula. Had to do a little bit of cleanup in the exponent position, a little bit of thinking about minutes to hours, but much easier relative to finding this one. So problems will often be given that lean more towards one model than the other, but they can all be forced into any kind of form. You could model this data that they gave us with any base, really. I mean, it would be tough, but you could do that if you wanted to, and it would look ugly. But the two best forms are going to be, and the two most natural questions for population are going to be questions about, like, when does the population double, right? And that's when this model is going to be the most natural, and versus what is the population's growth rate relative to its relative to its current population, and that would be this model. So two very natural questions and two very natural formulas coming from that, but you can always use both of these. It just, one way is always going to take a lot more algebra than the other. One way is going to be a lot more natural than the other. So that's what the point of this problem was. In fact, if you went and graphed these functions, they would be identical. They would be lying right on top of one another. Of course, there would be a little bit of discrepancy because I did have to round this number. If you recall, that was an irrational decimal number. But if I wanted even higher accuracy, I could just keep more of the digits. What was it? Yeah, this number here, this decimal number, I could just, if I wanted more accuracy, I could just keep more of those digits. If I wanted perfect accuracy, what would I do? I would literally, instead of writing this number here, this approximate decimal, I would literally write this entire log thing, which would be, it would look awful up there, but if I wanted it to be perfectly exactly the same as this model, this is what I would write up there, this whole natural log thing. Which would be, it would be a lot to look at, but it would be a perfect match to this example now. But I think for this problem, rounding to the fourth decimal place is just fine for this rate R. So this is where, math really gets useful, especially I think most of you guys are majoring in biology and stuff. I'm guessing that what would happen in your biology classes is these models would already be built for you in the data. I don't really know. I mean, but because I've never taken a biology course. But just know that when you're running data and you're getting this data and people are saying, extrapolating and saying, this is how much the population will be after this amount of time, these are the models that are telling them that, right? This is where the math gets applied, at least one little area where math gets applied in biology. Of course, we're just scratching the surface, like barely scratching the surface here. The models can get way more complicated and the data can get way more complicated. Anyways, okay, so that finishes all of the material that we're going to cover this semester. A few things. Let's see, what do I need to say? The section 1.6, you may have seen that in your WebAssign homework. It's just a bonus assignment. It's one of those topics that is nice to get to if we have time, but we didn't. I could have forced it in there, but I decided not to. So it's just there if you decide that you feel good about the final and you're not feeling real stressed and you feel like you have time to study something new to get a few extra bonus points, then you can do that. It's basically solving radical equations and rational equations. So you might have even done that in high school, so you might already know, or at least have an idea of how to do it. But if you're just want to focus on studying for the final, then just forget it. Don't worry about 1.6. It's not going to hurt your grade. So Friday, we're going to talk about it would be real good if you came to our meeting on Friday knowing what we were going to do if you were already kind of fresh on it. So solving quadratic equations is one of the most important things that you should walk away from this class knowing how to do. Solving quadratic equations, that was section 1.4. Now remember that we had a lot of tools for this section, but the main tool that always works, but you got to know how to use it, is the quadratic formula. Whoa, that's supposed to be a 2. That's a 2, 2a. And that is for quadratic equations of this form, where there's a 0 there. Okay, and the a, b, and c you see in this formula are coming from the coefficients of the quadratic equation there. Or well, yeah. So that is going to be on the final, and also transformations of functions, transformations of function graphs, transformations. It's 2.6. What did they actually call it? 1 second. Just okay, transformations of functions. Couldn't remember if they said function graphs or just functions. So we're talking about what, if you've got a function f of x equals x cubed plus 1, what does that look like? What does the plus 1 do? What does the base function look like, right? So in this case, an x cubed graph looks something like this. And what does the plus 1 do? So you got to recall the plus 1 is going to scoot it up by 1. So that would scoot it up here by 1. So go look at those and recall what those different rules were for adding and subtracting outside of a function, scoots up and down, adding or subtracting inside of the function, so inside the parentheses, like in the input of the function, that's going to be a horizontal shift, and all those rules. So it would be great if you went and looked at those and recalled what those were, at least glance at them before we review on Friday. That would help a lot. Oh, that's section 2.6 if you need to know where that is in the book. Also note that in our chat here in Teams, there are problems for you to look at from the text. So you go to your ebook in WebAssign and go look at those problems and make sure you know how to solve them before the final exam. And don't forget your WebAssign, about your WebAssign as well, because that's worth a fair bit of points. So don't forget about that for chapter 4. Okay, if you guys don't have any questions about what we're going to review or the 2 examples I just covered, if you need me to say anything else about those examples, I'd be happy to do that. But otherwise, you guys are good to go.